So before we begin, I want to warn you, this is code all the way through, so come forward if you have trouble reading the font size. That's about as small as it can be. I hope we're good. All right. Differential Dataflow. What is that? That is a computational structure. Who has heard of React and used React? Everybody, right? So React is a different computational structure, also for user interfaces. So what this talk is about the computational structure of user interfaces. But instead of giving an abstract slides talk about this, I'm actually just going to teach you electric, and then concretely, by learning electric, we're going to learn about the computational structure that electric encodes, which is the structure of user interfaces. Okay? So let's jump right into it. This is the 2 clocks demo, and what we have, let me get my brush. We have a clock on the server and a clock on the client, and we're subtracting them. Okay? So to encode this in electric, it's a 12-line program. This is the whole program. And you have these client and server markers, so there's front-end and back-end parts, okay? So this system time MS is a clock on the server, and here's another clock on the client, bound to CNS, and then we're subtracting them right here. Okay, so what eDefn does is it is a Clojure macro which is compiling this unified program into a client-server system. So there is a front end, there is a back end, okay? And then there is a WebSocket between them. The server parts compiled onto Clojure, run on the JVM, obviously, and then the client parts compiled onto ClojureScript, which runs in the browser, okay? This here is the ClojureScript subtraction operator because we're on the client, okay? So that's regular subtraction. Now keep in mind, S and C are reactive variables, okay? They vary in time, they're changing. So these are an asynchronous reactive type under the hood. So this subtraction expression here is being auto-mapped over the underlying async type, which is a missionary signal, okay? So essentially what electric does with this macro is it analyzes this ClojureScript syntax, Clojure and ClojureScript, with a custom ClojureScript analyzer and compiles it down to a DAG, and we use the DAG to orchestrate and automatically generate the reactive FRP code under the hood, which is being auto-mapped by the compiler, okay? All right. The DOM is effectful via point mutations. So there's not React, there's no virtual DOM, and you don't need a virtual DOM because electric is fully reactive as a programming language. It's made Clojure itself fully reactive, so you don't need React. So to think about how this works, you can think of UIs as streaming DAGs. So a DAG is a directed acyclic graph. So you take these let statements and you say C, okay, when the client clock updates, the C variable updates, and you can think of the DAG as here are the edges that are downstream that the C depends on. So then you update the subtraction. And on the server, it's no different. The server clock updates, the S updates, there's a message over WebSocket right here, and then the S is used downstream in these 2 places. So you can see the DAG, all right? Now this is important, so let's take a closer look at the DAG. Let me make this a little bigger. So let's draw the program as the electric compiler sees it. We have S, there's a clock on the server, and it's used in these 2 places. So server here and server here. And then the C signal, there's a clock on the client here, and it's used in 2 places. And then the result of the subtraction is used to update the DOM. So that's here. So this is a simplified version of the DAG. So what electric needs to do at this point is basically ask itself, well, what parts are on the client and what parts on the server? So it will draw this box using these client-server markings and say, okay, this is on the server. I don't like that color. There. So I'm going to draw that same box right here. So basically, the compiler will graph color this and draw this exact box. And when you look at this, it is now very clear where the network crossings are. You can look for the crossings, and that's a WebSocket hop. So when the server clock fires, a message will come over network, and then the client will receive the message, and the client, based on the DAG, the directed graph, will propagate forward to the next expression that needs to run. So what the DAG is giving you is 2 things. The DAG is giving you reactivity. It tells you when this thing changes, what's downstream that needs to update next to stay consistent. And the DAG is also driving the network because by coloring the client and the server parts, we can very clearly identify the network crossings. Okay? So remember, UIs are streaming DAGs. Let's look at a more interesting and complex example. Okay, this is the Durtree demo. And what this is going to do very quickly is we're going to talk about like request waterfalls and request response because that would be slow. So we're going to loop over the server file system, over just a folder on the server using recursion. And while we recursively loop over the file system and render this tree, we're going to render it to the DOM in mid-flight. And we're going to do this in one recursive traversal, not two, okay? A single unified traversal. So we have a search thing, and here is the DOM input. So here is the search. Note that there's not a callback here. The DOM input returns the state of the search. Okay, so this is a pure functional callback-free pattern. Search is a signal that is reactive to the current state of the search box. Let me change colors. Okay. We've also got the file on the server. It's a Clojure Java IO file, so there's the folder we're looping over. And the file handle is passed here, and the search is passed here. And remember, the file handle is a Java reference. It's not serializable, so it could not possibly transfer to the client. Okay? So we call it into this electric function. So we have the file handle on the server and the search on the client. Okay? And on the server, we have an if statement, if the file is a directory. So you can do that. It's not the file is on the server. You ask if it's a directory on the server. And then you do the if statement, and then you switch to the client. You render the LI, you render a text node in the DOM, but what goes in the text node? You need the name of the file, so you switch to the server and you do the getName method call, which it's on the server. You can't have that data structure on the client. You want the native method. So now back to the client, render a UL to open a list, switch back to the server, get the children of the file on the server. Okay, loop over the children on the server, and now call recursively, re-enter the function, again, server client. Okay, so back to the top, is the file a directory, and so on. So if you are like me, you're probably terrified right now of request waterfalls. Okay, that is not what's happening here. Remember, UIs are streaming DAGs. So let's look at it as a DAG the way the compiler sees it. So you've got the file handle on the server, and you've got the is directory call on the server, okay? So you can run this call on the server without any client knowledge. Same with the if statement is on the server. The outcome of the if statement is known on the server. It's true. So the server knows this code is not going to run next. We're going to enter this frame right here, okay? Now, the eClient marker is static to the compiler. The compiler can see through this, and it can see in this branch of the cond, there's a server portion here where you have to call this method on the server. Now, again, this method has no client knowledge is needed to call this method except for the file handle and the outcome of the cond. If the cond is true, this is definitely going to be needed. So the server will anticipate this from the DAG and send down the result of the getName effect to the client without the client having to ask for it. Does that make sense? And so on. It works here. You render this on the client, but you don't need, the server isn't blocked on this. The server can continue to enter this and do the list files method. Again, it doesn't need client knowledge to do it. And then it can loop over the children of the file system and recur. And this can all happen synchronously because there's no causal knowledge on the client needed to do this. So in fact, this will be synchronous. The server will perform this recursive loop synchronously and eagerly without any waiting for the client and just stream it all as it's available. And then the client will receive the messages and then continue propagating the client portions of the program. And there will be no request waterfalls, no round trips. At least that's what we promise. We're getting pretty good at this. It's very close. Okay. All right, so at this point, that's just a demo just to clarify that this isn't request response. So then the next question is, how far does this scale? Like, how does this work in real apps? Because there are a bunch of ceilings in front-end technologies that we've seen, and not just front-end, like object mappers and ORM and GraphQL. These technologies all have ceilings, and they create abstraction problems. So here is a list of problems that I've encountered as a consultant doing enterprise user interfaces. And some of them are really obvious, like we need a solution to reactive rendering. We need a solution to the server connection. Okay, and request waterfalls, we just talked about that. That's pretty obvious. But some problems you don't see until like you start to scale. So resource disposal, how do you dispose of a resource you don't need anymore? Or query cancellation, what happens if The client is streaming information really fast and faster than the server can respond, and you want to skip to latest. And then you get to like back pressure and virtual scroll and streaming updates and optimistic updates. It's just really hard. So what we're going to do for the rest of this talk is we're going to go through a series of examples of an electric that are motivated by these problems, okay? And we're going to see the computational structure that solves this problem and how electric expresses it, okay? All right, so next we did request waterfalls. We're going to do resource disposal. All right, new demo for disposal. So what we have here is a blinker component. It's blinking. There's a DOM H1 in the DOM, and here it is, blink. There's a clock. When the seconds are even, you have this is-even signal. Now remember, this is a reactive is-even, so it's stateful. It varies. It's switching between true and false, okay? So if it's even, you want to mount this function. You want to put the DOM H1 in the DOM and put the text node in the DOM, okay? But what happens when the clock switches false? If this is false, the if statement switches false, and we need to dispose of this and dispose of all the resources that it allocated, which means dispose of the DOM text and dispose of the H1. So the way electric will do this is it will propagate a disposal signal backwards through the DAG. The DAG tells you in what order to mount things, but if you run that backwards, the DAG also tells you in what order to dispose of things, okay? So what we have here is automated resource disposal based on your causal dependencies based on the DAG. This is what electric gets you. So what about something more interesting than like a DOM element as a resource, something that's disposed of? How about a network connection? So what if right here, instead of saying blink, we switch to the server and add another clock. So I'm on a 10-year-old laptop that I just woke up from sleep. This better work. I don't know, it's taking so long. Oh, I have to log into my own system. Oh, shit. All right, we're going to have to imagine. Okay, this is less impressive with that working, but what happens is you get the clock. You see the clock here streaming like we did in the 2 clocks demo. And so think about what happens. You mount the blinker function, you mount the DOM H1, you mount the DOM text, you send a message to the server, you allocate this on the server, the clock resource. And when the if switches, you do it backwards. You dispose of the clock resource, you dispose of the client subscription to the server clock resource, you dispose of the DOM text, you dispose of the DOM H1. So UIs are streaming DAGs. The DAG is what gives you the resource disposal. And the automatically managed network connections. So this is how electric automatically manages your network connections. So that's resource disposal. Now let's talk about query cancellation. So we need a new demo for this one. This is come on. This is a T-short orders demo, a very simple like enterprise query. So you've got a list of T-short orders in a database, email address, gender, and the shirt size. And it's reactive to the text input. So here's the text input. The search state is on the client. You've got a database on the server. You pass the database on the server, the search on the client, server client. You've got this T-short orders query, server client. We're going to look at that in a second. You've got the result, the 3 IDs. You render the table, you loop over the IDs, and then you like query the form out of the database, and then you render the rows of the table, okay? So let's look inside of the T-shirt orders query, which is here. So database server, search client. On the server, let's do this inside out. You have a Clojure function, which is querying datomic server client. So this is the first time that we had to like do an effect on the server, on the JVM. It's an actual Clojure function. We're doing interop from electric to Clojure. So for this reason, the search from the client has to be realized on the server for the first time in order to call this Clojure function. So because this is encoded in the DAG, the static knowledge, the client will just automatically send the search as fast as it changes. The server doesn't have to ask for it. So every time you type into this, you'll get a new value of the search, and this query will rerun. Okay? What offload will do is this query is potentially slow, so electric, even on the back end, is a fully reactive asynchronous computation. So you don't want to block the async computation, so you have to offload your blocking effects to a thread pool. Okay. What happens if I'm typing very quickly and the query is slow and I'm typing faster than the database can keep up with? What happens is the client will eagerly stream the keystrokes as I type them here, and they show up here, and electric will rerun the query, but the old query might be still running if it was slow. So what offload will also do is will automatically dispose of the old query, interrupting the thread and disposing of any resources it allocated because it's been superseded by the new query, because you always want latest. Okay? So this is the value of automated resource disposal that electric gives you from the DAG. Okay, it lets you transparently dispose of this. And this is important. One of the mistakes front-end technologies make is they ask you to debounce your inputs. So, like, what if you want to avoid bursting the server with a bunch of queries as fast as I type, and maybe I'm typing quickly? What you're doing is you're slowing down the system and adding like 300 milliseconds of artificial latency to your responsiveness, okay? And that's really bad. What you want to do is you want the front end to send up information as soon as it becomes available, and the server will do its best to keep up, disposing of superseded things that you don't need anymore, and that way the server can be responsive. You just want to cancel old queries and supersede them. So that's a value of this abstraction. Okay, so that's the query cancellation problem. Let's talk about Lambda. I'm going to do this very quickly because we're constrained for time, but here is a Lambda. A Lambda is like a DAG as a value, higher order DAG. It like encodes like a mini DAG that you splice into the program when you call it. So all we're doing here is for this type ahead, there's like a pick list of options, and it's all filtered on the server based on this. So you only want to call this function when the pick list is open. So in the type ahead, there is an if statement. If is open. If it's open, you call the options callback with the search value from the client. And here's the search from the client. The electric function is booted, and it sends the search to the server into the query. So you get a responsive reactive query. So there's Lambda. Lambda works. I'm going to skip control flow for time. Maybe we come back to it. Let's talk about dependency injection. Okay, to do this one, we're going to use the Tudo MVC demo. So first, most Tudo MVCs are a front-end only abstraction. In Electric, we have this e-server to switch to the server, and basically 0 lines of code is free. So this is a server and client full stack Tudo MVC. So you get the multiplayer. If this guy transacts to the database, he will subscribe to the query and get the changes. And you got the styles, et cetera. So Tudo MVC is not the point. The point is that we are modeling Tudo MVC as a function. So if Tudo MVC is really a function and Electric really gives you functions that cross the client and the server, what's the way we can test this? One way I like to test this is give it the list test, which is if you're telling me it's a function, then you can call it a bunch of times in a list, and that should work. Okay? So let's do that. I've staged the demo for this. I'm going to expand the cardinality of this loop. Oh no, my hot code reloading is busted. Oh, that's such a bummer. Well, what you would see is you get the 3 Tudo MVCs staggered. I don't know if you've seen the demo online. It's online. And they would all be lively. They're all interactive. And it works. App is a function with client-server resources. Let's look at the code a little closer. So since this app is a function, like you get function laws. So here is your app as a function, and we're using partial function application to bind the database on the server and the state on the client. And we're partially applying this function, so you get a thunk right here, which you're passing into this popover cascaded function. And what that's doing, you can't see. It was doing like a staggered CSS layout, so you could see the 3 Tudo MVC apps. And then you just splice in the function right here. So the point is it's actually app as a function. These are real functions. This is functional programming, even though you're crossing the client and the server boundary. Okay. So that is dependency injection. So we're going back to the t-shirt orders demo to do the differential data flow. So as I type, we're running this query, right? Here's the diff by. Now, since we've all used React, we know there needs to be diffing somewhere in the system because you want to stabilize your writes to the DOM. And React does this at the very last moment. You get the virtual DOM, and you diff it, and then you reconcile. What Electric does is it lets you move the diffing as far upstream the DAG as possible so that you only do it once, but you can do it on the server. And what that does is it gives you diffs on the wire. You get differential network traffic because you've done the diffing on the server. Okay? So what that means is diff_by takes a function. This is like your React key. So if this query returns 9, 10, 11, and the query evolves, and we lost Alice and Charlie, right? You strike these. What you get is a negative diff. You get like a change set that describes two subtractions. So diff_by will diff the previous and the next collection value from the database, and you get a change set right here. Okay? So here, this is actually not a collection of IDs. This is a stream of diffs, an asynchronous stream of diffs. What for is doing is it is statefully accumulating over the stream of diffs to materialize the changes to the view. Okay? So when I clear this and Alice and Charlie came back, you got a positive change set of plus Alice plus Charlie, and the E4 will materialize Alice and Charlie and materialize them in the DOM. So the only place in userland where you have access to the full collection is in the DOM. In the Electric program, it is actually a stream of diffs. So I was going to show you the diffs, but I don't want to risk it. Let's move forward. So that's incremental collections. Okay, next is back pressure. Okay, so this is a project we did with Ben, who is here. This is a shipyard crane that is loading cargo onto a boat, okay? And it is a robot, and this is a digital twin observability UI for this robot. And what it's doing is it's streaming events from the robot through the cloud into this playback UI. Okay, so you can see at the bottom this playback UI, and you see the events from the robot. They're streaming through. Now we're actually also recording and logging the robot and saving the log. So this playback UI, you can actually pause and fast forward and rewind. So now we're playing it backwards, rewinding at like 40x speed, okay? So if you look here, you can see traffic streaming in at the edges because the playback UI can't keep up with the crane, okay? So this is the back pressure problem. How do you keep your system responsive when it can't keep up? Now, if you think about what if you just stream all the events to the UI, well, since it's going at 40x speed, you couldn't possibly do that. You'd have to drop events, and it would corrupt your system state if you drop events. So what you need is a way to skip ahead to latest. So differential data flow to the rescue. What we do is we switch from events to diffs. Okay, so you maintain this collection in memory, this windowed collection, which you're windowing over that robot log in the back end and diffing the collection. Okay, in diff squash, if you have like a git pull request and you have a bunch of commits, you can squash them all together into a single change set. So if the client can't keep up, the server will just reduce into a state. It'll accumulate the diffs into a single change set, and then when the client is ready, it will just get like a chunkier change set so that it can skip ahead to latest. Okay? So that's the secret to differential data flow. It gives you the back pressure semantics you need to decouple the client from the event rate of the server, which can be really fast. So this is important in scaled user interfaces. So given this, we can now talk about the infinite scroll demo. So if you have differential network traffic and streaming diffs, you might say, okay, well, how do I do a virtual scroll? So first, you need to get the offset limit from the DOM. So as I scroll this, there's an offset limit. And you need a strategy. You're going to stream the offset and limit to the server as they change, and then maybe you feed it to a SQL query and you pass the offset into the query. Or in this case, what we're doing is we're actually querying over the file system. So there's no database. So we're just sequencing the file system for this folder into an array, and we're windowing over that array in memory, which is like a 10 microsecond operation. You can window over this array. Okay? And because then you do a diff by over the window, you get change sets, And therefore, as I scroll this, you get a change set, you get differential network on the edges. So only what's on the screen is in the client device memory. It's disposing of the things you don't use, all automatically, all transparent. So what happens if you scroll abruptly? Say you drag this down, okay? What you'll see is there's not a lot you can do to reuse past states and get an incremental update if you've abruptly scrolled and jumped, right? You've lost you need to reload the viewport. But differential dataflow naturally happens that. You just get a big change set which has 50 rows in it. So based on how smoothly or abruptly you scroll, and based on the available resources and network bandwidth available, we will saturate your resources with the most graceful and small fine-grained diffs and change sets that the system can handle. And if your system can't keep up, you will just get coarse granularity change sets. And this happens gracefully. Now, of course, in order to do this, you cannot be debouncing your inputs, for example. You really need the client to send up latest, and then the server needs to dispose of things that, I was working in this query for you, but you've scrolled down, I don't need it anymore. This all needs to be transparently handled. And if you look at the code for a virtual scroll, I don't have it here, but it doesn't change your program. All these back pressure semantics and the diffing, it doesn't add weight to your program. It's just the same electric program. How am I for time? 2 minutes? Okay. So why did we do all this? We did not build electric or even conceive or think of electric on purpose. We were trying to build a low-code platform. If you follow Silicon Valley, there are drag-drop UI builders that have hundreds of millions of dollars of revenue, okay? So, and they don't work. They don't solve all these back pressure problems and the control flow and the dependency injection. They do a terrible job of this, and you get buggy, glitchy apps that don't scale. So we're trying to build a low-code application platform with a strong, rigorous composition model that allows you to connect to any server resource into your low-code platform. So the idea is, what if you have a Git repository, for example? This is coded in JGit using the Java Git API. We're waiting for JGit to query the file system on my 10-year-old computer. That wasn't electric. And you want to see the Git log, and you can query these backend data structures, these JGit Java method calls, natively from a UI, and you can get this data browser UI where you just navigate backend data structures natively. These are native Java method calls. And it can be for anything. So what you do is you take the electric server endpoint, and you're an enterprise. You have 10,000 microservices. You put it into each of your microservices, and once you put our agent there, we can call those functions in a high-frequency, high-fidelity way from a scalable UI that has all of these problems solved and frees you to have abstractions that compose across the boundary of all your microservices. So in order to do this, we had to build electric because you need to solve the supervision problem. You need to have efficient virtual scroll, and you had to have differential wire traffic because of back pressure. You get the reactive updates. So this is how we ended up deriving electric from first principles in order to attack this other larger market. So I'm Dustin Getz. This is electric, and the electric team is all here. They're around. Come talk to us. Thank you.